Hello YouTube. This one's gonna be longer. So I guess let's get cracking. We're gonna be talking about angular momentum. Angular momentum is actually a little bit more of an involved concept than rotational angular energy in a lot of cases because the directionality of it really matters. And that directionality gets a little weird when you have to actually care about right-hand rule. You can also get some kind of counterintuitive things because sometimes objects won't be spinning and then they'll hit something and they'll start spinning because they hit it. So for example, if I'm in a spinny chair, if someone threw something at me this way and I caught it, I would start to spin when I caught it. So that can lead to some weird stuff. The last final thing is that for normal momentum, mass can't really change for an object unless you combine with another object, but even then you're really just having two objects stick together. Rotational inertia can, and rotational inertia really can. So you can wind up in a lot of situations where you can have one object that significantly changes how it's moving without interacting with any other objects. And so it gets harder to model. So that's what we're going to be doing today. Ideally, at the end of the day, you should be able to model how objects change motion when they're spinning, in particular when they're interacting with other objects and when they're changing their shape. So using conservation of angular momentum to predict the results of an object changing its shape, first place to start. Using conservation of angular momentum to predict the results of spinning objects that are sticking to each other, or if you have spinning objects that are hitting each other and sticking, and then also using conservation of angular momentum to explain some aspects of gyroscopic motion. I don't have the wheel for that one, so unfortunately this is going to be more of an in-person thing. Ask about that, and we do need to talk about it. Just ask in person and we can go over it a bit more. So what is angular momentum? Well, angular momentum is how difficult it is to stop something from spinning in the specific direction that it's currently spinning. If you have positive angular momentum, it means that you are spinning forward. If you have a negative angular momentum, it means you're spinning backwards. Just like regular momentum, angular momentum is conserved in the absence of external forces, but in this case, external torques. So if nothing from outside a system is providing a torque on the system, then there you go. Angular momentum is a bit weird because it can have a direction, but the directions are counterintuitive for most people. The wheelchair demo is on here, but I don't have the wheels, so we're not doing it. And similarly with the figure skater demo, I don't have a convenient set of weights to do this with, so I kind of won't. But there's this, I can describe them a little bit. There's this really weird property of wheels where if they're spinning, and let's say the wheel is spinning this way, then its angular momentum is going to be up. And if you take that wheel that's spinning that way and you flip it from this way to this way, in order to do that, you will have to give it a lot of downward angular momentum because its angular momentum used to be going up, but now if you turn it around, its angular momentum will be going down. And so because of that, you will have needed to get a lot of upward angular momentum. So if you take this wheel that used to be spinning like this and you flip it over, now you'll start spinning in the direction that the wheel was going in order to conserve that. And it's really weird. Angular momentum also depends on your rotational inertia. So what I mean by that for this one in particular, or your moment of inertia, is that if you have an object that is spinning and you bring that object from out to inward because you have drastically reduced the rotational inertia because you've concentrated the mass much closer to the pivot, you'll wind up going a lot faster because your momentum stayed the same, but your mass effectively, or your inertia, decreased. That's not possible unless your speed increases, and so you can wind up spinning a lot faster without actually changing your mass. And so it's weird because it can feel like in a lot of cases rotational inertia is not being conserved, angular momentum is not being conserved because it's kind of counterintuitive to have a situation where speeds can be varying rapidly like that and still have your angular momentum be conserved. So that is something to watch out for. So equation for angular momentum is somewhat predictably, we take momentum, which previously had a stupid letter, so of course it still has a stupid letter. Angular momentum is capital L, which equals moment of inertia, capital I, times angular velocity, omega. So this is sort of the equation where not a single letter in it makes a single bit of sense, unfortunately. The thing, and this is something that I've mentioned a few times, but I is harder to find than mass, and so this equation can get more complicated because of that, but then also mass is conserved, whereas moment of inertia is not conserved. It's not a constant quantity of the universe. So you can very easily change the moment of inertia for an object, even though it is very difficult to change the mass in a scenario. Sometimes you do actually have to care about the relationship between linear and angular momentum. So in particular, if you have an object that is moving sideways and hit something, and they like stick together and spin, or they bounce off it and one of them starts spinning, or you get a situation like that, your angular momentum still needs to be conserved. And so you need a way to represent and think about this object that's moving linearly and do it with you need to think about this object that's moving linearly and relate that to and bring that into an angular momentum scenario. And the main way that you can do that is with r cross p, where p is the linear momentum and r is the momentum from the place where you want your pivot to be. This works for any pivot point, but you have to keep the same pivot point everywhere throughout the problem, which is weird because r will constantly be changing. And because it's a cross product, only the tangential velocity to that moment arm will matter. So you'll have to sometimes do things like mvr sine theta to keep track of it. So if you have an object that's moving in a straight line relative to a pivot, r will constantly be changing because you'll be getting closer to that pivot. Additionally, Vt will constantly be changing because as that object moves closer to the pivot, how much of its velocity is tangential or not is going to change. If the object starts infinitely far away from your pivot, you're effectively going to be pointing at the pivot because you are so far away that all space looks like a line. When you do get closer, the closer you get, the more your velocity will function as though it is tangential, and the less it'll function as though it's radial, so the bigger your angular momentum will get. From that perspective, and the bigger your angular momentum will get from a radius being but the smaller your angular momentum will get because your radius will be smaller. So this can behave in like some pretty weird and not necessarily intuitive ways. So just, I guess, make sure you're doing the equations. You can only use this equation set for point masses though, So do be careful, because if you're trying to do this with a large object, you're probably barking up the tree, the wrong tree. So first example, let's say we've got a person of mass m standing halfway to the edge of a merry-go-round with a mass of 2m and radius of r. The merry-go-round is spinning with an angular velocity of omega. How fast and in what direction would the person need to run to make the merry-go-round stop? Well, let's find out. So we've got our situation where we've got our person on a merry-go-round. Merry-go-round's got a mass of 2m. Person at a point of 1/2 r is going a velocity we don't know, while the merry-go-round is going with a angular velocity of omega. So, if we're going to make it so that our merry-go-round stops spinning, just realize that we need to look up the angular, the moment of inertia equation for a disk. We're going to need to make it so that we go from having whatever angular momentum the disk has to having all of that angular momentum get transferred over to the person. So in order for the disk to gain negative angular momentum, the person is going to have to be given positive angular momentum by the disk. So they're actually going to need to run the same way that the disk is spinning. Because if they run the opposite way that the disk is spinning, they'll be pushing the disk forward to push themselves backwards and gain negative angular momentum. So, going back a bit to get my handy dandy reference sheet, the rotational inertia of a disk, that's salt cylinder, is in fact 1/2 mr squared. Great, didn't remember that correctly. So what we're going to need to do in this case is figure out, well, what was the initial angular momentum for the disk? And then what we can do is set that equal to the angular momentum that the person will need to get, because they need to basically steal all that angular momentum away. And then figure out what the velocity of the person will need to be in order to make that happen. Well, the angular momentum of the disk is going to be equal to the moment of inertia for the disk times omega for the disk, which is omega. Well, I for the disk is equal to 1/2 mass of the disk times the radius of the disk squared. And, oh no, this is not focused. Hopefully it's visible on YouTube. Does it get better if I turn the light off? Weirdly enough, it just might. Alright. Oh, that shadow's annoying though. Alright. Well. Hopefully not having it directly on the page helps both get the shadow lower, and no, that makes it worse. Trials and troubles. Alright, well I think that's as good as we're gonna get for now. So if we take our moment of inertia for a disk and we throw it in, then the angular momentum for a disk, which is going to be equal to the angular momentum that we get the person, will be 1/2 times 2m, the mass of the disk, times the radius of the disk squared, times the velocity of the disk. The person is a point mass. So they're going to have an angular momentum of mvr. If we want to prove this out, the moment of inertia for the person is going to be mr squared. The angular momentum for the person is going to be equal to their tangential velocity divided by the radius, because omega r is equal to tangential velocity. Those two thankfully drop. I do have to be a little bit careful. This is mass of the person, the velocity of the person, and the radius of the person. And the radius for the person is going to be 1/2 of the actual radius. Great. So at this point, what we can say is that this angular momentum the disk starts with is equal the angular momentum that the person gains. Something to be a little bit careful of here. That's going to need to be equal to the angular momentum they gain, not the angular momentum that they have, because they start with the same initial velocity as the disk. So the change in their angular momentum will need to equal this. Their original angular momentum will be based on omega for the disk as well, where they had the same angular momentum as the person. As the disk. But we need to use their initial angular momentum to do this calculation. So if we want to find the angular momentum of the person now, it'll be their initial plus their change, which is equal to their initial plus the angular momentum that's stored up in the disk. The angular momentum that they had to start with is going to be I times omega. Their I is going to be m 1/2 the radius squared plus the angular momentum from the disk, which is 1/2 times 2 times r squared times omega. And that'll need to equal their angular momentum now, which is going to be equal to m 1/2 times the radius times their velocity. So, oh, right, because tangential, yes. So, mass drops, let's start there. If I remember to put it in every term anyway. This 1/2 and this 2 cancel, that's so nice. This 1/2 squares, and I do need to include the omega here. So we've got 1/2 r tangential velocity equals 1/4, because 1/2 squared, r squared omega plus r squared omega, which is equal to 5/4 r squared omega. And we can take that and multiply each side by 2, divide each side by r, and we're done. So our tangential velocity will be equal to 10/4 or 5/2 divided by r, so just r omega. So based on the radius of the merry-go-round and based on the speed merry-go-round is going. So things that were a little bit weird about this one that I honestly didn't anticipate initially. We have to make sure that we include the starting velocity that the person had, because they didn't just start from nothing. They had some angular momentum. And from there, then we need to give them the angular momentum that they're actually taking away from the wheel. If you take a look, the wheel's got a lot more angular momentum than them. Despite its shape concentrating more of its mass closer to the center, because them bringing half of their mass all the way in toward all of their mass halfway to the center is actually makes a much greater, greatly reduces their moment of inertia. So they have a much lower moment of inertia, which means, I guess 4 times lower, but they have a much lower moment of inertia, which means that even though they're initially going at the same speed as the wheel, they have a much smaller angular momentum to start. All right, angular impulse. So you can change momentum. And pretty much all you have to do to find that change in momentum is take the torque and multiply by the time. So just like you could take the force and multiply by time, or take a force versus time graph and use that to figure out about linear change in momentum, you can do the same thing with angular change in momentum, but with torque and time. The more torque you have on the object, the quicker the thing will start to stop or start moving. The quicker the thing will stop moving, or the quicker the thing will start moving. The more time you take it to do it, the less torque you will need. This can also happen with an integral. So you can also just do the integral of torque with respect to time, and it'll work just the same. So in a non-calculus example, the first Ferris wheel had a had a mass of, I should have put units on that, 12 million kilograms? I think I did kilograms. And a radius of 38 meters. And went about 5 meters per second at the edges. How much force would have been required to bring the wheel to rest? 20 seconds. If the force is being applied at the edge of the wheel, when I for the wheel is about 5/6 mr squared, because most of the wheel is most of the mass is calculated at the edges, but not all of it. Concentrated at the edges. And B, how much energy would need to be dissipated as heat. So, we need to provide enough torque to stop the entire thing from moving. So we need to take all of its angular momentum, get rid of it. So to do that, we need to say that we need to know what our angular momentum was that we're getting rid of. That change in our angular momentum will need to be equal to the torque that's being applied multiplied by, not a cross product, multiplied by the time that it takes to come to rest. So if we're trying to find the force, what we can do here is expand out that torque into an equation that actually includes force. R cross F. Well, it's being applied at the edge of the wheel, so R. It's perpendicular to the wheel. Great, so we don't have to worry about that. Times our time. Cool. All that's left now is to deal with our angular momentum. Well, angular momentum is equal to I omega. We are given the tangential velocity of the wheel. Omega times r equals our tangential velocity, dividing each side by r. Our omega is going to be our tangential velocity divided by our radius. Our I we're given is 5/6 mr squared. So plugging those two things in here, we'll get 5/6 mr squared times our tangential velocity, which is a given, divided by our radius. Cancel, cancel. That will need to be equal to our radius times our force times our time. Radius can be canceled from both sides, divide by the time, and we are done. So, 5/6 times mass times our tangential velocity divided by our time, which is 5/6 times our mass times our velocity divided by our time. So we've got 5 million divided by 2, which gives us 2,500,000 newtons of force required from our brakes to stop it in 20 seconds, which, yeah, big numbers for a big wheel. For part B, we're trying to figure out how much energy needs to be dissipated. Well, to figure out how much energy we need to lose, we need to figure out how much energy it had to start. EK is equal to 1/2 I omega squared. Same setup with omega. So we'll got 1/2 times 5/6 times m times r squared times our tangential velocity divided by squared divided by our radius squared. And so we'll get 5/12 times 12 million bonk bonk times radius squared times 5 squared, which will give us 1, 2, 5, 1, 2, 3, 1, 2, 3 joules worth of energy, which is an insanely high number because this thing was massive. So, plugging in for our moment of inertia again, plugging in for our omega using this equation here to get our answer. And it's just that's the amount of work we needed to do because work is basically the same thing as energy. Yes. Next example. Braking force on a wheel is modeled by negative AT squared while the wheel is stopping. How long would it take for the wheel to stop? From a velocity of v0 in terms of v0, m, and r if the wheel is approximately a hoop with brake force applied at the edge of the wheel in terms of, oh my gosh, well, I just said in terms of twice, and I feel mighty silly about that, but worse things have happened and will happen. So, we've got a situation where we've got a wheel, we've got a force applied to the wheel, where that force is equal to negative a t squared. I swear I didn't mean to make this a differential equation. I am so positive that a is supposed to be a constant. Because if it's not, this problem's going to be absolutely horrendous. Sorry. Great. So we once again have a situation where we need to start with all the angular momentum that it has and take away all of the angular momentum that it has. So, all of the angular momentum that it has at the beginning will need to equal the integral of the torque that's on it times, with respect to time. Well, we better figure out about torque. Well, torque is equal to r cross f, and if it's a perpendicular force that's slowing it down, you can do negative constant times time squared times r radius. Take that, pop that in for torque. For our angular momentum is equal to I omega. Well, I is equal to mr squared for a whoop, and omega is not a given, but we are given the tangential velocity of the wheel, and we can divide that by the radius. So, plugging that all in, we'll get mr squared v naught over r equals the integral of a constant times r times time squared dt. R cancels, both r's on both sides drop, and we're left with m v naught equals, we don't have to worry too much about this negative. We're applying a negative force, we get a negative torque, we're going to have a negative change in momentum, and that'll be coming from our negative torque. So those two drop, and we don't really have to care. A t to the third over 3 evaluated from our initial time to our final time. So we'll get m v naught equals a t to the third over 3. Multiply each side by 3, divide each side by a, multiply each side by 3, divide each side by a, and then raise each side to the 1/3 power to get rid of our cubed. And our final answer is 3 times our mass times our initial velocity divided by our acceleration to the 1/3 power is equal to our time. In theory, it's possible that I had meant to set this up as a differential equation where a stood for linear acceleration. I highly doubt it, though. what you would do in that case is you would have to model the linear acceleration and then set up and solve a very weird differential equation, because you need to find a way to get acceleration solely as a function of time. Which is beyond the scope of this course. So A was supposed to just stand for some constant. This is what I get for making these slides weeks in advance and then not actually doing the video when I made the slides. Yep. Oh, final example. A 40 kilogram student is standing on the edge of an 80 kilogram merry-go-round with a radius of 2 meters at rest. Another student throws a 5 kilogram medicine ball at them at a 10 meter per second velocity tangent to the merry-go-round. Okay, we've got our disk, we've got our point mass. What is the angular velocity of the system after the collision if they catch it? What is the angular velocity of the system be after the collision if the ball bounces off their hand at the same speed it was originally going? How and why would the answer change if the student had been changing in the middle of the merry-go-round? And how would your answer change if the ball's velocity had been radial? So, let's get this copied down. We've got a 40 kilogram student, so we've got M, we've got a merry-go-round of mass 2m, we know the radius, so M equals 40, R equals 2 meters kilograms, M B equals 5 kilograms, and velocity of the ball at the beginning is equal to 10 meters per second. So for A, we are trying to find the omega if catch. For B, we are trying to find omega if bounce. For C, we are trying to find how will that change if the student is standing in the middle of the merry-go-round. And D, if velocity is radial. Let's do it. So, omega if they catch. Well, if they're catching, then let's keep track of which objects have which momentums at which times. At the beginning, the only thing with, sorry, I just got a very painful cramp in my foot. At the beginning, our only object with any angular momentum is our medicine ball. And it's an object that's moving linearly and still has some angular momentum as a result. So we'll say that our angular momentum for a ball at the beginning is our only angular momentum at the beginning. At the end, they're all stuck together. And they're all sharing that angular momentum. So momentum at the beginning equals momentum at the end. Great. Well, momentum at the beginning will be mv times r. We've got our angular momentum for the ball. good. That will need to be equal, mass of the ball. That will need to be equal to our total angular momentum at the end times our omega. Well, we've got mass of our ball, velocity times radius equals our total angular momentum. Well, our total angular momentum is our disk plus our person plus our disk has a mass of 2m plus our ball. Mass of ball times the radius squared times omega. So this is the moment of inertia for disk, which has a mass of 2m, the moment of inertia for the person, and the moment of inertia for the ball. Thankfully, all we've got to do is divide, which I'm going to write as I total. And all the rest of these are givens. MBV over R divided by 1/2 2m R squared plus mR squared plus MB R squared omega. Okay. Nope, equals omega. So our 2 here drops, and we're left with our mass of our ball, which is 5, times the velocity of the ball, which is 10, divided by our mass, which is 80. 40 is m times our radius squared, 2 squared plus 40 times 2 squared plus 5 times 2 squared. So that'll get us 50 over 4 times 40 plus 4 times 40 is 80 times 40. 4 times 8 is 32, with 2 zeros, plus 25, or 5 times 4, which is 20. 2, 2, 0. Which is going to be very small indeed. All right, B. How is our situation different if it bounces? Well, 2 major changes. If it bounces, we're going to have some negative angular momentum from the ball going the other direction right after the bounce. We're also not going to have the ball attached to the other 2 objects. So our situation is going to look really similar. But we'll also have a negative angular momentum for the ball that's going to be the same as it was originally, but negative. And when we find our total angular momentum, it's going to be for the person plus the disk instead of the person plus the disk plus the ball. So if we add LB to both sides before we do anything here, we'll get double the angular momentum for the ball. Needs to equal our total angular momentum of our total objects. Double the angular momentum for the ball will equal 2mvbr, which will equal our angular momentum for the 2 objects instead of the 2 objects and the ball. And now we can just divide. So unfortunately for this one, and I'm gonna divide by I again, just so I don't have to write out as much stuff. Unfortunately for this one, we don't get a nice, easy linear relationship between these 2 things. Our omega will equal 2mvbr. Oh, I forgot the r in the last one, times 2, so 10 over 3. 322. And that'll be divided by 1/2 times 2 times m squared plus mr squared. So this time, there's only two big differences, which is that we've got double the change in momentum. We don't have this tiny little extra term added on to our final our final moment of inertia. So our final answer for this one will wind up being pretty similar. We'll double the numerator divided by close to the same denominator, which is 1/16. So we'll have just over double because we're both dividing by a smaller number and have a bigger number as our numerator from what we did originally. For C and D, our lowercase r for the angular momentum for the ball would be 0 because it's in the center of the circle where it's getting caught. So we actually wouldn't cause the thing to rotate, we'd cause it to slide. Or more likely, we'd just cause the ground to have to absorb the momentum. And similarly for D, it's R cross P. That cross product means that it's the tangential component. If it's a radial velocity, there's no tangential component. So it would be 0 for the beginning as well, and once again, we wouldn't get the thing to rotate. You can also think of it as how the ball would wind up pushing the person. The ball would wind up pushing the person in a way that wouldn't generate a torque, either because it's pointed at the center or it is from the center, and in both of those cases, you get no torque. Oh, that one was a doozy. Bye, YouTube. Oh, actually, you know what? Worth saying, we didn't do any problems where something changes its moment of inertia, and that's why its angular momentum changes. But you can do I1 omega 1 equals I2 omega 2, and you can get some really quick ratios that way. I'd recommend doing a problem or two like that, because that tends to be what can show up on multiple choice problems, because it's a quick, easy thing that just sort of tests, do you know how to do this? Yes, no. And they like things like that for multiple choice. Bye!